Everybody, we're going to talk about section 4.3, which is just making some connections between the first and second derivative with the original function. Okay, we need to talk about the first derivative test for local extrema, which is technically what we did. We've already learned that places where you can find maxes or mins must always occur at places where your derivative is either 0 or undefined. Okay, we're going to talk a little bit though about shelf points, and I want to bring your attention to this spot right here and also this spot. Notice that as my function increases, it levels out here to where we could still say we have a horizontal tangent. And so that just basically means we could kind of sit an egg on that spot and it wouldn't roll off. It's level enough that it would sit there. But then after that, it continues to increase. There is no maximum there. We call that a shelf point. And it's the same thing over here. Okay? He just decreases, levels off, and then continues to decrease again. Okay? And so we're going to be able to tell those easily using our sign charts with the first derivative. And basically the first derivative test is just finding the derivative, setting it equal to 0, finding those places where the derivative is 0 or doesn't exist, and then making our sign chart and drawing some conclusions from that accordingly. Okay, so we need to discuss right now this issue of concavity. Let me erase these things. Okay, concavity is technically talking about the bend of the graph. And if you look at this place here, this interval, you can see any tangent line I put into that piece is going to have a placement of sitting on top of the function. And so we would call that function over that interval concave down, and sometimes in class we'll refer to that as being frowning at that spot. But if you look over here in this section, do you notice my tangent lines are all on underneath my function? And so we would say that that function interval is concave up, and sometimes in class we'll talk about that being someplace where it's smiling. We're going to find concavity by looking at the second derivative. Okay, if the second derivative is positive, then our function is concave up over that interval, or smiling. If the second derivative is negative, then the function is concave down, or frowning. Okay. We also want to discuss points of inflection, and our point of inflection right here is that x equals 0 spot right there. And that's just meaning that's where our function is changing concavity. It's either changing from frowning to smiling or vice versa. You always look at your second derivative, and we're going to find where the second derivative equals 0 and where it doesn't exist. But you must look to see if it changes sign. If it does not change sign, we do not view that as a point of inflection. Okay, so we do have to create a sign chart for our second derivative to find points of inflection. So let's just jump right in and do an example right now. We're going to identify all extrema and points of inflection, and we're going to determine where this function is increasing and decreasing and where it's concave up and concave down. So the first thing here we need to find is our first derivative. Okay, so I'm going to do that off to the side over here. So our first derivative I'd need to find using the product rule. So that would be first d last plus last d first. And I'm going to clean that up by factoring. I see my two big groups here, and so I see that they have an x squared in common. So I'm going to pull that out, and that will be a negative x left here. And then I would have a plus 3 times the quantity 4 minus x when that guy is factored. And then cleaning up that inside piece, that would give me a negative, oops, he's got to distribute in. And so that would be negative x plus 12 minus 3x in that piece. And so we have here x squared would equal negative 4x plus 12. I'm going to go ahead and pull a negative 4 out front, so I have negative 4x squared times the quantity x minus 3. Okay, so off to the side over here, I'm going to write my first derivative as being negative 4x squared times x minus 3. Okay. Now we need to find our second derivative. because that's going to tell us things about the concavity, information about our function and his bend. Okay, so I have here my second derivative is also going to be found using the product rule. Okay, so second derivative here. Oops. First, the last plus last, the first, negative 8x. And when I clean that up by factoring, I'm going to look at that and say that they each have a negative 4x in common. Okay. And so that will leave me with a positive x here and a positive 2 times the quantity x minus 3 here. And cleaning that up, negative 4x. I'm going to distribute my 2 in, so that will give me a 3x here minus 6. And I'm going to go ahead and GCF out a 3, so that will be a negative 12x times x minus 2. So there's my second derivative. I'm going to leave them in factored form because they're just a lot easier to work with. Okay, so now we need to just find where it's increasing and decreasing. And so we're going to do set our first derivative equal to 0. And so we can see that my first derivative equals 0 by setting those quantities equal to 0. So that will be at x equals 0 and also at x equals 3. Okay, so we're going to make a sign chart. 0 and 3. And I'm going to plug values within those intervals back into my first derivative. Okay, so I'm going to put negative 1 back into my first derivative. A negative 1 here is going to give me a negative, and a negative 1 here is going to give me a negative, and a negative times a negative is a positive. Okay, and then I'm going to pick a 1 for this interval right here, and when I put 1 in there, I'll get a negative here and a negative here, so he is also positive. And then I'm going to pick a 4 for my last piece. That'll give me a negative here and a positive here. A negative times a positive is a negative. Okay, so what's nice about this is right off the bat I can tell that this right here is going to result in a shelf point because it's increasing and then increasing. Okay, whereas this guy right here, because we're changing from increasing to decreasing, that spot x equals 3 would result in a maximum. Okay, so we would have I'm just going to write this over here, an absolute max. And I know it's absolute because of my original function being an x to the 4th. Okay, so the maximum I find is going to be the absolute. So we have an absolute max at f of 3. And that value, when I put 3 back into my original function, will be 27. Okay, and then I'll just have a shelf point at x equals 0, and so we don't need to state that as any kind of extrema. Okay, and we can also tell from this sign chart where our function is increasing or decreasing. Our function is increasing over the interval from negative infinity to 0, along with 0 to 3. And some books will allow you to go ahead and go from negative infinity to 3. And on the AP test, it really does not matter because some books just define increasing and decreasing functions differently. I will accept either in this case. And then we will have decreasing from 3 to infinity. And all that information was taken from our sign chart for the first derivative. Okay. Well, let's see what's going on with our second derivative. And so I'm going to do green here. How's that sound? So my second derivative is equal to 0 at, let's see here, at 0 and also at 2. Okay, so we're going to make a sign chart for that. I'm going to pick a different color because that's really hard to see. Let's just go with black. Okay. And so in this case, if I pick values and put them back into my second derivative, let's pick -1. If I put -1 in here, that's going to be a positive. -1 in there is going to be a negative. Positive times a negative is a negative. If I pick 1, 1 in here is negative, a 1 in here is negative, a negative times a negative is a positive. And 3, a 3 here is negative, a 3 here is positive, a negative times a positive is a negative. So we have 2 points of inflection. We do in fact have one at 0, and we do in fact have one at 2. So we're going to say, I'm running out of room here. Let me just erase this piece up on the top. So we would have a point of inflection at f of 0. When I put 0 back in, I get 0. And then also at f of 2, when I put 2 in, I believe I get 16. Okay? And then we can also tell here where the function is increasing or concave up. It's concave up where our second derivative is positive. And so that would be over 0 to 2. And then it's concave down over -infinity to 0, as well as 2 to positive infinity.